Welcome once again. Next topic we are going to see is process concept. Okay, I think all we know what is meant by process. Process is nothing but a program in execution. We call that as a process. Okay, a program which is ideally saved in the computer is called as program, whereas the program in execution is called as process. In operating system, it executes variety of programs. In batch systems, the variety of programs it executes will be called as jobs, whereas in time shared systems, it is called as user programs or tasks. In test books, normally it is termed termed as jobs and process. Okay, so these are the words which are used by these type of systems. Batch systems, they'll say as jobs. Time sharing systems, they say as user programs or task. So process, as I said, a program in execution is called as process. The process execution must progress in sequential fashion. Then multiple parts of a process is the program code, which is also called as text section. We call that as text section. Then current activity, which includes program counter, processor registers, then stack containing temporary data, where the function parameters, return addresses, local variables are stored. Then data section will be there containing global variables. Then heap, which will be containing memory dynamically allocated during runtime. So these are the multiple parts we have in process. Then program is a passive entity stored on your disk. That is executable file, say for example add.c, which you store in the hard disk is called as program. Whereas if you want to execute that by giving control alt delete or something for compiling and execution, you have some commands. If you give that, the program will come into the main memory and it starts executing. No, so that is called as process, which is a active entity. Program becomes process when executable file loaded into the memory. That's what I'm saying. Memory in the sense it is called as primary memory. Then execution of program started via GUI, mouse clicks, command line entry of its name, etc. Execution can be done using a mouse click or a command line entry. Then one program can be several processes. Don't think that a program is a process. So one program can be seen as a several processes. Consider multiple users executing the same program. Then so this is a process in memory. The it will be like text section, data section, heap, stack. Then what are the contents which we have in the process? So these are the process which is stored in the memory. Then process states. Next, coming on to the process states. What are the states it goes? Okay, a process when it is executed, it changes its states normally. Okay, a process when it is taken for execution will changes its states. These have 5 states actually. One is new state, then running state, waiting state, ready state, and terminated state. So new state, when we call a process is in a new state means the process is being created. Whenever a process is created, it is in the new state. Then running state, instructions are being executed when the instruction which are present in the process are executed, it will come into the running state. Then waiting state, if the process is waiting for some events to occur, say for example if it wants some IO devices, it will wait for some time, so that at that point of time it will come to the waiting state. Then ready state, the process is waiting to be assigned to the processor. So if the process is ready, then we can say that it is waiting for the CPU to take over. Then terminated state, the process has finished execution. Whenever the process has finished the execution, it comes to the terminated state. So these are the 5 states we have in a process. So this is the diagram which shows the process states. Okay, so here the new state is there when it is when the process is created, it will be in the new state. When it is ready for execution, then it comes to the ready state. When it is running, that is executing, then it is in the running state. Whenever it wants some IO or any event completion it wants to do, then it comes to the waiting state. Then when the whole process finishes its execution, then it comes to the terminated state. Then we have a block called process control block, which is also called as PCB. I think you all heard about what is PCB, process control block. So information associated with each process will be stored in the PCB. Whatever information which is associated to each process will be there in the PCB. Means what is the state of the process, then process number it have, then program counter, what is the value we have in the program counter, registers, what are the registers it is using, memory limits from where to where it is using, list of files open. So these are some of the information associated with each process. So it will be stored in the process control block. So here process state means whether it is in a running state or waiting state or it is in a terminator state, like that the state will be mentioned there. Then program counter, location of instruction to next execute. So next what instruction must be executed will be in the program counter. Then CPU registers, contents of all the process centric registers will be there. Then CPU scheduling information, priorities, then scheduling queue pointers, everything will be there. Those type of information will be stored there. Then memory management information like memory allocated to the process, how much memory is allocated from where to where. Then accounting information, CPU used, how much time the CPU has uh, used this process or the process has been given to the CPU. Then clock time elapsed since start and time limits. So everything will be there in the accounting information. Then IO status information, that is the information regarding IO devices allocated to this process, when it is allocated and what are the IO devices it has been given, then list of files opened, everything has been there in the process control block. Then a CPU switch from process to process. How the CPU will switch from process to process? As I said, a program can be divided into many processes so that the CPU has to switch from one process to the other process. Here we have two processes, P0 and P1. Okay, the OS will be executing the P0 first. Then if an interrupt or system call comes, then the state of that process will be saved in the PCB and it will be waiting. Then process P1 will starts executing. When the process P1 wants to stop or a interrupt is given to stop, then the values of those has been stored in the PCB and it has to be juggled to the process P1. Like that, the switch will happen from process to process. Okay, so this is what is one of the major works of operating system. Then threads. So you have to know about threads. What is this thread and all? So for process has a single thread of execution. So process has a single thread of execution. Consider having multiple program counters per process. So if you have multiple PCs for a process, multiple locations can execute at once. So multiple locations can be executed at once at the same point of time. Multiple threads of control will be there. Must then have a storage for thread details, multiple program counters in PCB. So everything has to be stored in PCB. So it should have all those details stored in the PCB. Then, so this is how process will be represented in Linux. So it will be like this: PID, process ID. So long state, unassigned int, time slice. So everything will be initialized properly. So it will be represented like this in Linux. Then next, so this is the process concept we have seen. Then next topic we are going to see is process scheduling. So process scheduling means each process has to be scheduled for the CPU by the OS. So maximize CPU use. So that is the major motto. So you have to maximize the CPU utilization. Quickly switch between the processes. Okay. For that you need time sharing algorithms. So for a particular point of time, this process has to be given the CPU, and if the time completes, then it has to move on to the next process. Like that it goes on. The process scheduler selects among available processes for next execution on CPU. So what process has to be executed next by the CPU is the work of process scheduler. So it maintains a scheduling queues when the process is coming inside, when it has to be given for the execution, like that the OS has to perform. For that, it is going to maintain a scheduling queue. So there are three types of queues. First is job queue. Here all the set of processes will be in the system. All the process will be in job queue. Then there will be ready queue. Set of all process reside in the main memory. Ready and waiting for execution will be there in the ready queue. Wherever the process is ready for execution, it will come to the ready queue. First, it will be in the job queue. Then it will move on to the ready queue whenever it is ready for execution. Then device queue, set of process waiting for an IO device will be there in the device queues. So these are the main scheduling queues of a process. Sorry, we have three scheduling queues, namely job queue, ready queue, and device queues. Ready queue and various IO device queues will be like this. Queue header will be there in ready queue. Then there will be PCBs. Then to manage that. Then how much space it requires. Terminal unit 0. So what are the terminals it needs? So from where to where it is stored, everything will be there in the queues. So queuing diagram has been given. So representation of process scheduling will be like this. So here, see here, there is CPU, there is ready queue. Whenever all the requests, IO request will be then moving on to the IO queues. If there is any request for IO, it will move to the IO queue. Then it comes to the IO. Then it goes for ready queue for execution. Then if times slice expired, then it has to go to the ready queue. Then if you want to create any process, you need to give a fork command, fork a child. Okay, so then the child executes, then it comes to the ready queue. Then whenever the interrupt occurs, then the certain process is asking for CPU, so that it has to move to the ready queue. So this is the representation of process, how the process will move on to the ready queue and how it is given to the CPU. Then you need to know about schedulers. There are two types of schedulers we have: short-term scheduler and long-term scheduler. Short-term scheduler are also called as CPU schedulers, whereas long-term schedulers are also called as job schedulers. So this short-term scheduler selects which process should be executed next and allocate CPU. That is the work of short-term scheduler. So it is going to select the process from the ready queue and gives or allocates the CPU. Sometimes the only scheduler in the system, sometimes only short-term scheduler will be in the system. Short-term scheduler is invoked frequently. So it is invoked in milliseconds, must be so fast. So it is invoked frequently. Then there is a scheduler called long-term scheduler or job scheduler. It is going to select which process should be brought into the ready queue. So all the process will be in the job queue. Then this job scheduler's work is which processes has to come to the ready queue for execution. That is the work of long-term schedulers or job schedulers. The long-term scheduler is invoked infrequently. It will take some amount of time, say for example seconds or minutes it will take. Then the long-term scheduler controls the degree of multi-programming. Okay, so this is having the control of multi-programming. process that can be described as either IO bound process, CPU bound process. Process can be termed like this also: IO bound process, CPU bound process. So IO bound process spends more time doing IO than computations, whereas CPU bound process spends more time doing computations. Okay, so it has a very long CPU burst, whereas the IO bound process will have short CPU burst. Then addition of medium term scheduling. So one more scheduling called medium term scheduling is also there. Medium term schedulers works will be can be added if the degree of multi-programming needs to decrease. If the degree of multi-programming needs to decrease, this medium-term scheduler has to be there. It removes process from memory, stores on disk, bring back in from disk to continue execution. Swapping. The work of medium-term scheduler is swapping. Swapping from memory, main memory to secondary memory to main memory. So that is the work of medium-term scheduler. Then multitasking in mobile systems. What is this? Some mobile systems, example early version of iOS, allows only one process to run, others will be suspended. Okay. Due to screen real estate user interface limits, iOS provides for a single foreground process controlled via user interface, multiple background processes in memory running but not on the display with limits. Then limits include single short task, receiving notification of events, specific long running tasks like audio playbacks, etc. On-write runs foreground and background within fewer limits. Background process uses a service to perform tasks. Service can keep running even if the background process is suspended. So service has no user interface, small memory use. So multitasking in mobile systems will be uh, what restricted. Okay. Then finally you need to know about context switch. So when the CPU switches from another process, the system must save the state. So whenever the CPU wants to switch to another process, the state of the system or state of the process has to be saved, and which is called as old process. Okay, which is going to be taken out and load the saved state for the new process via context switch. So context switch will do what? It saves the state of the old process and load the saved state of the new process. So that is the work of context switch. So context of a process represented in PCB. Though this will be represented in PCB because all the information related to the process will be there in the PCB. Context switch time is overhead. The system does no useful work while switching. So while switching, the system will not do anything. The more complex the OS and the PCB, the longer the context switch. So if the OS is complex and the PCB, the longer the context switch. Switch will be take more time. Then time dependent on hardware support. Some hardware provides multiple set of registers for the CPU, then multiple contacts loaded at once. So this can be done. So this is contacts switch. Thank you.